Hello. So we've got a satellite. It's powered by solar panels, and it's orbiting around the Earth at about 10,000 kilometers, medium Earth orbit, and it has a power requirement. That power requirement is 5 kilowatts. That's quite a bit of power. Maybe it's a spy satellite. Um, it's got one other thing that we need to know about it is that the efficiency of the electronics on the satellite that changes when it's in the sun and when it's out of the sun, and that's because when it's out of the sun, it needs to charge off of a battery. All the electronics, it probably has some spy cameras, some telecom dishes, things like this, using a lot of power, and draining the battery is going to take more power than taking from the solar panels directly. So let's say the efficiency during the day is 80%, and the efficiency at night is 60%. So now we're thinking, how are we going to figure out how much daytime and how much nighttime it has every time it goes around the Earth? Well, we know a good equation. This is just the most fundamental equation from orbital mechanics, and this will tell us the period. So this will tell us the period of this is the radius of the Earth, this is the altitude, this is a gravitational parameter specific to the Earth. This tells us the period of how long it takes to go around the Earth, but we still need to know how much of that is sunlight and how much of that is nighttime. It's not half and half, you say? Well, let's take a picture. This is the sun. This is our little Earth, and it's shining light, of course, this way, and the light is shining like this, and that makes back here, let's see, what's this going to look like? It's going to look like, this is what the shadow is going to look like. And so say our satellite orbit is right here. That's a circle. You can see that it's definitely smaller than half of the time in nighttime. But the good news is we know the radius of the sun, we know the radius of the Earth, we know this distance, we know this altitude. So with a lot of trigonometry, it's actually definitely possible just to figure this out. The good thing though is we have tables, and these tables will not just figure out this angle for us, but it can actually just tell us what the period is and also what the maximum nighttime is going to be. So let's see, we said it's at 10,000 kilometers. Get a purple. For 10,000 kilometers altitude, we're going to have a period of t equals 347.66 minutes. The nighttime out of that period, when it's dark, is going to be 44.27 minutes. And of course, we can just get the daytime by the difference between those two, 303.39 minutes. And so definitely a lot more daytime than nighttime, which is good for our satellite. So now we just need to come up with some kind of equation that will take these numbers we have so far, and it's going to tell us, well, by charging a battery, how much power are we going to need to collect during daytime to hold us through during the night. Well, we can say, all right, let's go for one day, because we know it's going to be the same every day. Let's say the energy required for one day is going to be the same as the energy collected. And we know that the power needed during the day is going to be different than the power needed during the night. Power day, power night. The way an efficiency works is just going to be, we divide it by the daytime efficiency and the nighttime efficiency. If you do this, you will get 800, 333 watts, and 600, 250 watts. Difference we talked about before. And if we say, all right, well, P night, T night, the energy at night, plus P day, T day, this is the energy required, is going to equal the P collected, so the P array, times the time at day. So we have all of these values. Now we just need to solve for the power of the array, and that comes out nicely to be 7.5 about kilowatts. So that's how much power the solar panels need. We can use that, maybe get some sizes for them. We have a nice, well-sized SPY satellite solar panel.